In this video, we're going to analyze the behavior of a certain circuit, namely this circuit. This is a circuit with an input voltage signal here labeled as x of t, a capacitor with capacitance C, a resistor with resistance R, and an output function voltage as a function labeled as y of t. First, we're going to set up a differential equation which connects the function x to the function of y. And to do this, we're going to consider some nodal analysis in this node of the circuit. First, we're going to set a reference ground over here, so we can calculate the values of the voltages in the circuit. On this node, we have a voltage of y of t minus our ground, which is 0. And on this node, we have a voltage of x of t minus this voltage, which is ground, which is also 0. Next, we're going to consider the currents in this node. We have first an incoming current I0 and an outgoing current I1 and another outgoing current I2. Because of the Kirchhoff current law, we know that the incoming current into a node must be equal to the outgoing current of a node. So we find that I0 equals I1 plus I2. Because I1 is not part of a loop, we know that this goes to 0. So in fact, our Kirchhoff law just gives that I0 equals I2. I0, that's the current through the capacitor, and that's given by this voltage, by this formula, which is capacitance times time derivative of voltage across the capacitor, which in this case is this voltage minus this voltage, which gives us C equals D x minus y by dt. I2, that's just the voltage through the resistor, which can be found by Ohm's law. This states that the voltage across the resistor equals resistance times current. So the voltage across this resistor is y minus 0 equals y divided by the resistance. Then we equate these two things, then we get the formula x prime times c minus c times y prime equals y divided by r. We can massage this a bit around, and then we get the formula y prime plus 1 over rc y plus x equals x prime. Next, we want to find the transfer function, so we take the Laplace transform of this expression. Then we get that s times big Y of s minus the derivative of y in point 0 plus 1 divided by rc y of s. That's equal to s times the Laplace transform of x of s minus this the derivative of x value in 0. We assume that our initial conditions are 0, which leaves us with the formula y of s plus 1 over rc equals s times x of s. Next, to find the transfer function, we want to find y divided by x, which is easily found. That's equal to our transfer function, which equals s divided by s plus 1 over rc. This can be rewritten as 1 over 1 plus 1 over s rc. We are assuming that Rx is a pure sine wave, so we can say that S equals I times omega, where omega is the frequency of x, and then we get the expression 1 plus 1 over omega I rc. And now to find the behavior of y as we vary x, we consider the amplitude of this transfer function, which is given by this expression. Which equals 1 divided by 1 plus 1 over, or it should be minus 1 divided by 1 plus 1 over I over RC. This equals 1 divided by 1 squared plus 1 divided by omega RC all squared. And so our amplitude equals the square root of 1 over 1 plus 1 over omega RC squared. And now we want to find out the low frequency and high frequency behavior. So we take the limit as omega goes to 0, and we find out that if this gets really small, this expression gets really big, which in turn means that this whole fraction goes to 0. And if omega gets really large, to infinity, then we find that our h of omega, when this gets really big, this expression goes to 0. So this whole fraction goes to 1 over 1. So this goes to 1. And meaning that we have created a high pass filter here, since it blocks out all of the low frequencies and lets the high frequency pass through, hence the name high pass filter.